Hello and welcome to part 4. Slightly different question from usual. We're going to be working with momentum in a contextual question, not a standard collision question as we're used to with the previous 3 parts. So first off, we can draw a diagram. We have a bullet. I'm going to draw like so. We can call it B if you like. B for bullet. We have a mass of 0.008 kilograms and an initial velocity, so remember we do initial velocity with a U, of 330 meters per second. Hits object A, which has a mass of 20 kilograms and no initial velocity. Now it takes 1 millisecond for the momentum to transfer, which is the same as 1 times 10 to minus 3 seconds. And that's about it really, in terms of diagram, at least for now. So we need to find out the force acting on object A first, so the force exerted on object A by object B. So for that we need this formula, F equals delta P over delta T, where delta is change in, so the top of it reads change in momentum, and the bottom reads change in time, or time taken. Now, it is 100% transfer of momentum. So the change in momentum is the entire initial momentum of the bullet. So, using P equals mB, we can substitute P for mass of the bullet times initial velocity of the bullet divided by delta T. Just to clarify what we're doing here, we are going from perspective of the force acting on the bullet, or the force exerted on the bullet in order to stop it, in order to transfer all its momentum, which according to Newtonian physics will be equal to the force exerted on A. You could do it the opposite way around by calculating the final velocity of A and then doing it by using the momentum gained by A divided by time taken. You get the same answer, and it would require us to do the question backwards. So really it's up to you. But I'm going to stick with this way. So we put in the numbers, 0.008 times 330 divided by 1 times 10 to the minus 3. Now unfortunately I have completely run out of space, so I'm going to have to put my answer, well, not in the right sequence. I'll probably put it over here. F equals, have that ready. Let's put that into a calculator. 0.008 times 330 divided by brackets 1 exp minus 3 equals. And that gives me an answer of 240. So we write the answer 240. Let's try that again. Newtons. And that's part A done. Notice how I've set out the working. I started with my formula. There was no rearrangement, but if there was a rearrangement, that would be immediately afterwards. Substitutions, I suppose, count as part of the rearrangement, so I'll put that immediately afterwards. Then I put in the numbers, and the answer, whoops, and the unit. Make sure you follow that sequence, and you will always score all the marks available for a question, obviously assuming that you've got it right. So that's part A. Let's move on to part B. Now for part B, it's a standard momentum question as we're used to, but we just need to be able to see where the information is. Now that's where a diagram comes into play, because it allows us to see what has the mass of this, what has the initial velocity of this, and allows us to continue it. It says it's 100% transfer of momentum. Now this would insinuate that the bullet hits the object and stays separate. Now I'm going to make that correction into the question. Hopefully you've already caught that. So let's see what we have. So it's 100% transfer of momentum, so the bullet no longer has any momentum, so mass is still 0.008 kilograms, and the final velocity is 0, and object A still has its mass of 20 kilograms, and its new velocity, which we do not know. So hopefully this should be all pretty much second nature now. as to what we're doing. In fact, I don't know why I'm doing this, because I'm going to remove the bottom part of my diagram and find the total initial momentum. Okay? So, sum initial momentum equals m, well, we might as well stick to notation we've got, mbub plus mb, MAUA, apologies for that. We could stick the numbers in, but you know what, it makes the same difference anyway, because we know UA is 0, so we can cancel that anyway because UA equals 0. Therefore, sum of the initial momentum equals MBUB equals 0.008 times 330, which if we put that into a calculator, equals 2.64 kilogram meters per second. Now, you might think that's not a lot of momentum for something travelling so fast, but remember, a bullet has a very, very small mass. So it does actually make sense. Now we just need to continue. Remembering that the sum initial momentum always equals the sum final momentum, which equals, as we just calculated, 2.64 kilogram meters per second. Okay, so now we do to part B, remembering that the sum final momentum is going to be equal to the mass of the bullet times the velocity of the bullet, plus the mass of object A times the velocity of object A. Now, again, we know that's 100% transfer of momentum, so velocity B will be 0. So that whole bit cancels out. Therefore, we get sum of the final momentum equals MAVA. Don't need brackets. Therefore, rearrangement. We put in the numbers. The mass of A, of course, being 20 kilograms. So there's my answer from before. We divide by 20 equals 0.132. Meters per second. And that's it. That's the last numerical. Oh, just move it up slightly. There we go. So that's the last numerical question. Next part, and that's the final part for this series, is going to be talking about a relation between momentum of force and airbag safety. A very, very standard question on exams. Please do leave comments if you can think of any ways to improve it, or if you found a mistake. Hopefully you haven't. And if there's anything else you'd like me to do, I'm going to try and make these public within the next few days, seeing depending on what the policy is, etc. So possibly if you're watching this now, you might not even be of Notre Dame. Hello. Anyway, right then. I'll see you next part.